Okay, let's talk now about the action potential in the cardiac muscles. And actually, before going to the cardiac muscles, let's try to remember the action potential in the skeletal muscles. So I'll do some drawings here. So in skeletal muscles, if you remember, we have depolarization and then we have repolarization, right? If you remember, this is maybe it was around minus 70 or minus 70, and here it's plus 30. We're talking about millivolt. This is the membrane potential, and here is the time. And usually the time is around 25 milliseconds. If you remember the depolarization, because sodium gates open and sodium ions move inside. Here at this point, sodium gates closed, potassium gates open, and therefore we will have the repolarization due to potassium ions leaving. Right, so this was the action potential in the skeletal muscle. So what about the cardiac muscle? There are few differences between the two. And here we will see the action potential in the ventricle. In the atria, it's very similar. Okay, it's shorter, but it's very similar in the concepts. And since the most important ventricle is the left ventricle, so that is the one we are going to see its action potential. Why it's the important one? Because this is the one that pushes the blood to the body, right, through the aorta. So here we have resting membrane potential at around minus 90 millivolt. Okay, that will go up to around plus 30 millivolt, very similar. So this is the membrane potential, and here is the time. Now the first step, of course, is the depolarization. But instead of like a gradual depolarization, we will have very sharp depolarization. This depolarization is because of the rush in sodium ions. There is a huge rush of sodium ions. Like all of the sodium gates will open and the sodium would rush toward the gate. And it will reach around to the plus 30. At around the plus 30, that is where the sodium gates also will close. And from there, we will start repolarize. So once we start to repolarize, there is another gate will open. That will be calcium gates open. And calcium start to get into the cell. However, the calcium gates, when they close, they will close slowly. And technically, this drawing should be a little bit toward down, because we are going to lose the membrane potential. So here the calcium gates will open, and calcium moves inside, okay? But those calcium gates close slowly. And this gives us something we'll call the plateau. So the plateau is because of the slow closing of calcium gates. So what's happening here, we are gradually losing membrane potential, okay? Or moving toward repolarization, or gradually repolarizing the membrane potential. Gradually, and importantly, it's slowly. Now, why do we need this, the plateau? The plateau is to increase contractions intensity in muscles. Remember, we said we need to squeeze the heart from the bottom, and we are pushing the blood outside the ventricle. So that push, we are pushing the blood through the entire cardiovascular system, through the entire blood vessels in our body. So there is so much resistance there. So I need much more and powerful contractions. And that is where the plateau would come. It will sustain those contractions. It will keep the heart squeezed, or the muscles, the ventricle muscles contracted, to ensure that the blood is being pushed forward. Okay? So once we have this gradual loss of the plateau, at one point, we will have the potassium gates open, and of course calcium gates close, and that is where we will have the repolarization. So from the beginning, like time-wise, from here to around here, once we restore the membrane potential, we're talking about 300 milliseconds. The plateau itself, we're talking about like until here, maybe around 200 milliseconds. So the plateau maybe will take around 200 milliseconds, the plateau, to ensure that we sustain the contractions in the heart. So again, to recap, we have a very rapid depolarization. In the skeletal muscles, it was slow, not as rapid as that. at the top, sodium gates will close, calcium gates will open, but they will slowly close. And when they slowly close, this will cause slow leaving of the calcium ions. And therefore, the repolarization is going to be slow. Okay, and notice that we are above the positive value of the membrane potential. Then, toward the end, we have the potassium gates open, calcium gates close, potassium will start leaving, and then that's where we get the repolarization. Now, one thing also of the plateau is important because it's going to prevent further stimulation. So we have, during this period, no contractions. This will call it the refractory period. So during this period, for sure, no double action potential. Okay? No double action potential. And specifically this area, like from here to here, we'll call it the absolute refractory period. It means that no way we are going to get action potential here. Here, from here to here, we'll call it the relative refractory period. So here, what does it mean? It means in case of strong stimulation, we might start a new action potential. But definitely during this period, during the plateau, there is no way to get the action potential. So that's the action potential of the cardiac muscle. So if we want to overlap the action potential with the contraction, notice this area. The peak of the tension of the contraction is toward the end of the plateau. So what's happening here, we are building up the contraction or the tension. So squeezing, think of it like squeezing gradually, and we are maintaining that squeeze. Okay, so that is the idea of the plateau. To build up this tension, remember we said we need to push the blood through the entire arterial system of the heart. And there is so much resistance there. We're talking about the systemic circulation. So that's why we need like great deal of tension, great deal of contractions. So this would last, we said the plateau would last maybe like 175 milliseconds to 200 milliseconds. The tension, the contraction of the heart of the ventricle, will take around the 200 milliseconds. This is just for the ventricle. This is not the entire heart. This is just for the ventricle. Here and here, just for the ventricle. So with the skeletal muscles, we did not have much time there. The action potential there would last around the depolarization specifically would, very much less than in the cardiac muscle. We are talking about the entire contraction in skeletal muscles might, last between 15 to 100 milliseconds, depending on the how big the muscles. In the heart, it will take well over 200 milliseconds. Okay? In the skeletal muscles, the tension would increase with more stimulation. In the heart, the tension is the same, but if we want to push more blood, the rate of contractions would increase. Okay, I'll stop here. In the following video, we will talk about the ECG.